Bismillah Rahmanir Rahim. I am Hamad Shahzad and I am presenting my final year topic. Our project title is Life Cycle Assessment of Self-Compacting Concrete Incorporating Quarry Dust and Steel Mill Scale as Partial Replacement of Fine Aggregates. Our project supervisor is Dr. Adnan Nawaz and these are the names of my group members. This is the outline of this presentation which we will discuss. The aggregates and steel are the key constraints of the reinforced concrete. Aggregates make 70 to 80% of the concrete volume and steel is high in tensile strength. The manufacturing of the steel and crushing of aggregates generates waste products, which are steel mill scale and quarry dust respectively. These waste products are very harmful for the environment. These waste products must be used within the construction industry to achieve sustainability. Introduction to the self-compacting concrete. It is a type of concrete that flows under its own weight in a fresh state. That is why it does not require any mechanical vibration for its compaction. So there are reduced risk of segregation, bleeding and other defects. Problem statement. Quarry dust and steel mill scale, which are industrial waste products, are causing undesirable effects on the environment and hydraulic structures. Using them in concrete as fine aggregates may reduce their impact on the environment and can result in more durable and cost-effective concrete. The objectives of this research will include the determination of the effects of quarry dust and steel mill scale replacement on the properties of the concrete and to carry out the life cycle assessment of self-compacting concrete. Life cycle assessment is a systematic method to quantify the environmental profile of the product. The Sustainable Development Goals are the 17 goals which are set by United Nations to attain sustainable future. Our research will target the SDG 9, 11 and 13. Methodology. This slide shows the flowchart of the methodological process. We started with these mixed proportions, moved to trial mixes, did necessary tests for the self-compacting concrete. Then we tested the properties of the control mix and other mixes which we got from the design of experiment technique. We used Revit to determine the quantity takeoff for our life cycle assessment study. We did optimization of the concrete using the design of experiment technique and we did life cycle assessment using OpenLCA software. The design of experiment is a statistical technique used for the optimization of the responses. These are our mixed proportions. We made 10 mixes which we got from the Design Expert software. This slide showed the mixed design of the concrete according to the ACI 237R. These are the minimum requirements of the self-compacting concrete according to the code. Results. We observed maximum strength at 60% replacement level. The tensile and flexural strength were optimized for 30% replacement of the fine aggregates with quarry dust. We also expect higher durability values. This slide shows the relative compressive strength results. The strength of the control mix is taken as 100% and the strengths of the other mixes are compared to the control mix. There is 14% decrease in the compressive strength of the M6 concrete mix. This slide shows the compressive strength results in megapascal. This slide shows the relative splitting tensile strength results. There is 16% increase in the splitting tensile strength of the M5 concrete. These are the test results in megapascal. These are the relative flexural strength results. There are 50% increase in the flexural strength of the M5 concrete. These are the flexural strength results in the megapascal. Life cycle assessment methodology. There are 4 mandatory steps in the life cycle assessment listed here. These include the goal and scope definition, the life cycle inventory analysis, the life cycle impact assessment and interpretation. These are all done automatically by the OpenLCA software. We used Revit to calculate the quantity takeoff for the life cycle assessment study. These are our results we got from the 3D model in Revit. This is the plan and elevation of the 3D model that we developed in Revit. These are the impact categories for the life cycle assessment. There are total 18 impact categories in the recipe made point H method. These are the life cycle assessment results for the each impact category. These are for the control mix and M5 control mix and M5 mix. This graph shows the life cycle assessment results for the control mix and M5 concrete mix for each impact category. Socio-economic benefits of our product. The steel mill scale and quarry dust are the waste products. If we incorporate them into concrete, it will reduce the cost per cubic meter of the concrete. Moreover, the water pollution and the air pollution will also be reduced. We will also move one step closer to the sustainability. To conclude, the compressive strength, splitting tensile, and flexural strength of our concrete were increased up to 14, 16, and 50% respectively as compared to the control mix. 80% reduction in water depletion, 40% decrease in urban land occupation, 10% reduction in ozone depletion, 40% reduction of the natural land transformation, and 2% decrease in the global warming potential was also noticed as compared to the control mix. Thank you very much.